Hi, my name is Lee. This is my honor today that I'm gonna do a presentation for our teamwork of introducing a new algorithm named ChunkedHC used for the authorship verification task. The algorithm is tested on Reddit user data as our study case study. So talking about team as well why this paper exists at the first place. Half year ago, I was a master's student in Ireland and I was doing my master thesis at the time. The topic is this very topic. The MS paper submitted to the DFRWS conference. So my academic supervisor for my dissertation was Dr. Justin McGuinness. He is the lecturer at Munster Technological University, Cork, Ireland, and I really love his teaching methods. He supported me a lot while doing my master. The second person behind this work is Mr. Edward Dixon, who is now my boss. He's the founder of the Rig AI. He's really passionate about the forensic research as well as the sensitive data. You could contact him via his email for interesting discussions about forensic and sensitive data. Finally, it's me. Actually, I'm the machine learning engineer at Rig AI, also the lead author of this paper. Now, so let's talk about what ChunkedHC and what does it do. We started a very simple questions. There's many social network platforms like Facebook, Twitter, Reddit, etc. And how to know which accounts are duplicated. And why does it matter? Because finding true people behind fake accounts used for illegal activity is the objective of the academic researchers, industrial practitioners, and legal enforcement officials working in the digital forensic domain. So, into the objective of the paper is to identify whether two social media accounts belong to the same person by examining their comments and posts from two accounts. This is the authorship verification task. So authorship verification could be classified into intrinsic or extrinsic. So in this way, we focus on the intrinsic method. So there's gonna be different paths, approaches, but there's one problem. They all involve complex feature selection and sophisticated pre-processing steps. So is it the motivation for us to introduce our new algorithm ChunkedHC? And ChunkedHC is based on the statistical testing hierarchism and XC-based similarity algorithm. So the novelty of this study is going to be there's no need to pre-process text input as ChunkedHC consider all text elements, including characters, punctuation, and special characters. And ChunkedHC are not influenced by different topics and genres, and the algorithm is highly versatile and applicable to various contexts. The output is a similarity probabilities, which is directly derived from a pair of text without having additional information or datasets. So the computation is quite light as well. So here our research questions. Now we're gonna talk about first thing first, the theoretical foundation of the paper and the ChunkedHCs, the hierarchy system first. So it's a statistical test to test a very subtle problem from a large number of independent statistical tests. All of the null hypotheses are true, or some of them are not. Suppose we have the set of n p-values from p1 to pn. P1 is smallest and pn is largest. And the objective function and the axis statistics are defined as follows. When axes are large, the set of p-value is inconsistent of the global null hypothesis, which means there's enough evidence to support the global alternative hypothesis. From the axis objective function and the axis statistics, the index I star. So when the axis is maximum and corresponding with the t axis, which means the axis threshold, so are defined as follow. So it's gonna be very useful for feature selection in the classification settings. So we're gonna know in seconds. So talking about the next stuff, the next theoretical base for the ChunkedHC, which is the XC-based similarity algorithm. So there's going to be a lot of notation and equation for this algorithm, but in short, Gimlis 2020 proposed a binomial well allocation model, and to use that model to measure the distance between two documents by using the XC statistic. If the distance between two documents or the XC statistic is large, so two documents are different, and if the distance is small, so two documents are going to be the same. Also, here from the cutoff by calculating the XC statistics, he also derived the delta, which is the set of the author characteristic word. It's a very important property of the XC base similarity algorithm. So it's automatically focused on the author characteristic word rather than the topic words. The algorithm is robust and suitable to deal with the authorship tasks in different topics. Now, so it's the XC-based similarity algorithm summarized in the algorithm format. Right, so we're not gonna talk about the ChunkedHC the next slide. So now I'm gonna talk about the ChunkedHC algorithm, which is the meat of this presentation, the research. There's gonna be 3 steps. Step 1, chunking the text. Step 2, measuring XC distance between chunks and corpora. Step 3, estimating similarity probability. Now, talking about step 1. Given perhaps text 1 and text 2, each of them split into chunks of identical length of the characters. That length is going to be C. So, yes. Now, talking about step 2, we're going to measure the XC distance between individual chunks. Now, we have individual chunks of each of the text 1 and text 2. Let's say, in this case, text 1 is in red, text 2 in blue. Altogether is in this 2D coordinate, but I'm gonna explain to you why those individual chunks is placed in those positions right now. So we have like a TK is an individual chunk in this case. So you can see the yellow one here circle. The chunk, this individual chunk is the text to chunk, so TK. We're measuring the distance between this chunk with all of the kind of the individual chunks from text 1, so D1K, and also the D2K is these chunks with the rest against with its same kinds. I mean the blue one here, so D2K and D1K, we have those. And then now we compare the distance. If in this case D1K is larger than D2K, so it's gonna be classified as that TK is categorized as the C2 bread. And we're gonna do for all the rest of all of the individual chunks here, and we got this. So the number of C1 press plus the number of C2 press equal the number of C1 plus number of C2. Now what we're gonna do next, estimating similarity probability. Now, so after doing the kind of this classification, so separating, you can see here the diagonal line is where D1 is going D2. So for the rest, so above this diagonal line is D1 larger than D2. Those are gonna group into the C2 bread, and those below is C1 bread. And we can do we can have the confusion matrix among the actual classes and predicted classes. And we can derive from here the accuracy in F1 to calculate score, S score. Here in this case, the S score is ranging from 0 to 1. Now there are two possible extreme scenario in this for the S score. Let's say the text 1 and text 2 sample from two different authors. The first extreme scenario here is all of the chunk text are separated clearly, and then the accuracy and F1 in this case are both 1, and leading to the S desired difference is gonna be 1. So the another extreme scenario is text 1 and text 2 are sampled from the same author, and then all of the chunk text, all of the individual chunks are gonna be mixed up altogether. And then in this case, the accuracies and F1 are both 0 or 5. So in this case, we have S design similarities also 0 or 5. Now we have the S score here. So it's the average between accuracy and F1, and we can plot it into the graph like this. And the two extreme scenario, one is design difference and one is design similarity. And then we turn it into probability like this. So, and then we just a little bit kind of the transmission and the conversion here, and we do have we can calculate the probability similarity in this case derived from the S score. In this case, when P simi, which means the similarity probability, when it comes to 1, it indicates a pair. So the text 1 and text 2 are sampled from the same author. When it's the similarity probabilities approaching 0, so it indicates it's gonna, though text 1 and text 2 sample from two different authors. So the ChunkedHC algorithm can summarize like this. There might be 3 steps: step 1, step 2, and step 3. So the input is the step 1, the text 1 and text 2, and the output is gonna be the similarity probability. If that's gonna be 1, so text 1 and text 2 are sampled from the same author. If the similarity probabilities is approaching 0, so text 1 and text 2 are from different authors. Now talking about the experiments, and firstly let's create some dataset from Reddit. For one username, we gonna concatenate the kind of aggregate post and comment for that one username, so for his or her. So create a pair of two different authors by using two different usernames. So that's just the assumption they actually from two different people, because we cannot validate verify whether or not they are actually from the same or different people. So create a pair of the same author. So we just only use one username and split it into two halves. So now we're gonna create some dataset for surveying and testing. And surveying is gonna have the short text and long text, and testing is gonna mix range text. In our studies, short texts are considered having less than 10,000 characters, and long texts are more than 10,000 characters. For each of the interval, the number of pairs of similar and different authors are equal. And then, so for serving ChunkedHC is to find the perfect combinations of the vocabulary size and the chunk size. So to have the best performance that we could have for the testing. Now for surveying ChunkedHC, and this is for the short text, for text between 1,000 and 10,000 characters. This is the heat map for the AUC score for different chunk size and vocabulary size. First thing first, ChunkedHC have poor performance for chunk size of 100 or 200 characters, when it's only slightly better than random guesses. The AUC score is just above 0.5. Meanwhile, the largest chunk size of 3,000 characters offer worse performance than all the smaller chunk size. Interestingly, the combined chunk size of 500 characters with the vocabulary size of 20 most frequently used will provide the best result for the short text. So here is the 10 combination of the chunk size and vocabulary size, in which ChunkedHC has the highest AUC score for the entire short text dataset. So we can see that the short chunk size at 500 and 800 characters could be the suitable choice for text between 1000 and 4000 characters. For text between 4000 and 6000 characters, that's missing among the nominated chunk size. For text between 6000 and 10,000 characters, the chunk size at 2000 characters offer a good result for all cases shown. Now talking about the long text between 10,000 and up to 100,000 characters. So this is also the heat map for the AUC score for different chunk size and vocabulary size. The chunk size show poor performance for the shortest chunk size of 500 characters, with the vocabulary size of 200 to 1000 more frequently used words. The performance decrease when chunk size is greater than 8,000 characters. The algorithm seems had the desirable performance with the chunk size around 2, 3, and 5,000 characters. Now we're talking about the AUC score for individual intervals. So this figure illustrates the AUC score for the all-length interval from 10 combination of the chunk size and vocabulary size, where the algorithm has the highest AUC score for the entire long text dataset. So there's some few observations here. First, longer text correspond to higher AUC score generally. Second, the only subtle difference for the AUC score among the combination of the chunk size and the vocabulary size for all the intervals. In particular, the difference becomes smaller and smaller when the texts are longer. Now we talk about testing. So from the surveying the ChunkedHC, we just know the combination of the chunk size in the vocabulary size. Yes. So for the highest AUC score, now this session is testing the algorithm by using those accepted choice of chunk size and vocabulary size from the previous session. For the text from between the ranging from between 1 to 2,000 characters to between 29 to 30,000 characters. Thirdly, the selected values of chunk size in vocabulary size and the similarity probability is calculated for all the steps is step 1, and next the dataset is split into two equal halves, which are the validation set and the test set. For each interval, the validation set is used for selecting optimal threshold where the accuracy is maximum, and the final step here is. So we on the test sets, the threshold T is we use for to predict the positive and negative class, and then classification metrics including accuracy, F1 and AUC score are calculated for individual intervals. So overall, this session provides a detailed picture of the algorithm ability and its limit. Now talking about with the chosen, so this is the density plot or similarity probability distribution for all of the intervals. So with the chosen chunk size and vocabulary size, the similarity probability is calculated for all of the text pairs. This figure demonstrates the similarity probability distribution for the pairs of both similar and different orders. So there's few observations here. The text pair below 10,000 characters tend to have multimodal distribution. For text above 10,000 characters, so the similarity probability has the unimodal distribution. As the text gets longer, the distribution of the two classes become more and more distinct. Within the scope of this study, accuracy is the main classification matrix quantifying how well ChunkedHC identify pairs of similar authors. This is the basis for choosing the decision threshold, where the accuracy score are maximum on the validation set. This figure indicates how the threshold value changes across the text length. For interval between the 1 and 6,000 characters, the decision threshold are larger than the author threshold value. For longer text, threshold value seem approach to common threshold value at 0.5. So talking about the testing the ChunkedHC on the test set. So with the optimal threshold derived from the validation set, positive and negative classes are predicted on the test set. The table and the line graph show the AUC accuracy and F1 score for all of the intervals. Firstly, for the shortest interval between 1 and 2000 characters, the accuracy F1 are 0.6 around 0.645 and 0.67 respectively. For text between 5,000 and 10,000 characters, the accuracy is above 0.7. For longer text, the performance metrics increase. In particular, the accuracy F and F1 reach up to 0.94 and 0.93 respectively for the longest step between 29 and 30,000 characters. Now, we talk about discussion. The input. The algorithm does not need to require sophisticated pre-processing steps. The ChunkedHC could be theoretically suitable for other language like other and English, and also being suitable for other social media platforms such as Facebook, Twitter, etc. ChunkedHC might not adequately capture authors' writing style due to the distribution of the monograms. The underrepresented features would potentially cost the algorithm verification ability. So it's advisable to consider the imbalance class when applied in the ChunkedHC. So recommended, there should not be difference between the text element for the two text input. Avoid the bias in the internal binary classification for the output. So ChunkedHC directly provides similarity probabilities. 0 indicate a pair of different author, 1 indicate a pair of the same author. But in the most cases, it might be more challenging to conclude with less definitive probability values. So the basic obstacle for the authorship verification task is choosing a universal threshold distinguishing the positive and negative classes. So threshold might need to be adjusted for different datasets, also depend on other factors. Now talking about the performance. So ChunkedHC provide good results when text input are sufficiently long. It's crucial to carefully select the chunk size, vocabulary size, and decision threshold for different unique lengths. So from the empirical result, short text chunk size should be small, and decision threshold needs to be more conservative to value closer to upper limit of 1 for longer text. The chunk size should be approximately 2,000 to 3,000 characters with common threshold at 0.5. So for the runtime, the ChunkedHC is fast and straightforward without having training data phase measuring. The XC statistic has a moderate computational cost, and ChunkedHC will be slower with the longer text or having shorter chunk size with the larger vocabulary size. Now comparison with other approaches. ChunkedHC offers a much simpler workflow than machine learning or deep learning approaches. Nevertheless, it might come cost at the verification ability, such as ChunkedHC performance might not be as good as this. This is only the preliminary papers as the introduction to the ChunkedHC, and their algorithm was not fully compared with authorship verification approaches. So, talking about the conclusion and features of ChunkedHC and the algorithm specifically designed for the authorship verification task. So, the ChunkedHC is gonna give a similarity probability from 0 to 1. 0 indicate a different the pair of different author, and 1 indicate a pair of the same author. And then apply ChunkedHCs on the ready user data is gonna be, so the performance is gonna be much be improved for the text are longer. So especially so the accuracy is gonna be up to 0.94 for the text between 29 to 30,000 characters. And for the future works, so we're gonna grouping the rare word together, sharing some similarity, so mapping over to their corresponding part of speech task with some modification for the text input. This is the things our team not currently do in this show promising results, and optimizing the key parameters and also expand this study to other dataset and compare ChunkedHC to other approaches. Thank you for listening.